we're going to work with limits. And the definition of a limit says that if f of x becomes arbitrarily close to a single number that we will call L, as x approaches c from either side, from the left side or the right side, then the limit of f of x as x approaches c is equal to L. So what you need to really worry about here is just this terminology that this capital L stands for that numerical limit value. Now, in our work with limits, we're going to work with some properties that allow us to find the limits algebraically. So properties of limits, many times you can simply substitute, do some direct substitution right into your equation to find your limit value. Therefore, sometimes the limit as x approaches c of f of x is actually equal to f of c. For this to happen, we have to have some continuity going on, which is what we'll talk about in our next lesson. So we'll take it slow. Here are some properties of limits. The limit as x approaches c of a constant b is equal to that constant b. The limit as x approaches c of x, which is a linear function. So this is linear. So this is a constant function. So we'll call this a constant function. And we'll call this a linear function. Is equal to c. Now this linear function I should say with one term. I'll just say a linear function with one term. That'll be very clear there. Limit as x approaches c of an exponential function is equal to c raised to the n power. And then we have a radical function. Can't really say a square root function. A radical function. If your index is even, then c must be positive. Okay, so these properties are actually very, very helpful for you to have. C are real numbers, B and C are real numbers, okay? This right here would be a good idea for you to make some note cards with, these properties of limits, because if you know these shortcuts, and I know it seems maybe confusing now, but you'll use them later on. Now we've got some operations with limits. If we have a scalar multiple, the limit as x approaches c of f of x multiplied by that multiple is the same thing as b times L. So what they're saying here is you can find the limit as x approaches c of f of x. And if it is that f of x is being multiplied by a scalar, then you're just going to multiply your limit value by that scalar. What else is true is if you're finding the limit of the sum or difference of two functions, then you can find the limit of each one and add or subtract those limits together. If you're multiplying two functions together, you're going to multiply those two limits. If you're dividing, you're going to divide. And then the limit as x approaches c of a function raised to the nth power is the same thing as that limit raised to the nth power. So again, they're looking for the limit of f of x as x approaches c, and if that is raised to the nth power, then your limit will also be raised to the nth power. And the true is with the roots as well in number 6. Best thing to do is maybe get some practice with this. So let's do that. Let's get some practice. Finding the limit of a polynomial function. Big thing here is that you don't have any restrictions. So there's no restrictions. You have no denominator, you have no radical, you have no restrictions on the domain. We know that polynomial functions are smooth and continuous. You might have learned that in your college algebra class. Polynomial functions are smooth and continuous. Therefore, polynomial functions, we can find the limit using direct substitution. Direct substitution. So this is the rule that's going to work here. The limit as x approaches 2 of x squared plus 2x minus 3 is equal to 2 squared plus 2 times 2 minus 3. 4 plus 4 minus 3 is 5. And it's that simple. Okay, let's try another. So you go ahead and try this, and when you're ready to reveal the answer, press play. Now I'm going to tell you something here. I'm ready to reveal the answer, but I do think it's a really good idea, especially in the very beginning, that you rewrite your problems down so you get used to how to write them. The limit as x approaches 1 of 2x squared minus x plus 4 is equal to direct substitution. You're going to take the 1 and you're going to directly substitute it in for x because polynomial functions are continuous. And it's going to allow us to find the limit because the limit is going to equal the function value at c. And I got 5. The limit of a polynomial function is exactly what we just said. As x approaches c, p of x is equal to p of c. Sometimes it's not that easy to do direct substitution. And I'm going to give you an example. Now, this replacement theorem is something that you could come back to and after we do the problems, and you'll make sense of it. I'll make sense of it for you. Okay, finding the limit as of a function, and the function is x cubed minus 1 over x minus 1. So I'm going to rewrite this. The limit as x approaches 1, and I'm just going to put this in parentheses, of x cubed minus 1 over x minus 1. If I try to use direct substitution, I'm going to get a 0 in the denominator, and a 0 in the denominator is undefined. Therefore, what we have to do here is we have to factor, and that factoring is going to eliminate the problem in the denominator. Don't you just hate it when there are problems in the denominator? Well, we just get rid of them. And this is how we're going to do it. We're going to factor. So we're going to factor this out. So I've got the limit as x approaches 1 of x minus 1 times x squared plus x plus 1 all over x minus 1. And now you can see that the x minus 1s are going to cancel, and now we can use direct substitution. So we're going to take this 1, and now we can substitute it in, and you can see that there's no denominator that's causing a problem. So when we do that, we get 1 squared plus 1 plus 1 is equal to 3. So our limit as x approaches 1 of x cubed minus 1 over x minus 1 is equal to 3. Now for you to try. Make sure you press pause, and when you're ready to reveal the answer, press play. Okay, welcome back. So what we have here is I've factored the numerator to be x minus 2, x squared plus 2x plus 4, and the denominator is still 2. Now we have that denominator canceled out. We can do direct substitution, which is 2 squared plus 2 times 2 plus 4, which is 12. So if you got 12, you got it. Here's another one for you to try. It does say example, but I think that you can try it. So let's try this one. Press pause, and we'll see if you've really got it. And if you do, you're going to be feeling really good about yourself. And welcome back. And if you try this one and you got -5, you got it correct. We factor, we get rid of the problem in the denominator, and then we do direct substitution. Here's one more for you to try, and I'm going to let you try it. The limit as x approaches 3 of x squared plus x minus 12 all over x minus 3. And we're back and ready to reveal the answer. And if you got 7, then you got it correct. Okay, so now I want to go back to what I was saying earlier. I'm going to go back a couple of pages. Let c be a real number and let f of x equal g of x for all x not equal to c. If the limit of g of x exists as x approaches c, then the limit of f of x also exists. And the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x. So basically, what we had was, we had this example. So x cubed minus 1 over x minus 1 is equal to the simplified version, x squared plus x plus 1, as long as x is not equal to 1. And that's exactly what we did. We got an equivalent expression, not an equal expression, an equivalent expression. However, x could not equal 1, and that's exactly what c was. So x could not equal c. See, here's your c right there, that's your c, and x was not equal to that c. So that's exactly what it meant. It just meant reduce your expression. And so be it. Now, dividing out is not the only example. There's another technique in which we use a lot in calculus, and that's called rationalizing the numerator. So in this example, we are going to rationalize the numerator. We are going to rationalize the numerator. You're used to rationalizing the denominator for a completely different reason. Before we had calculators, we rationalized the denominator so that we could divide without a calculator. However, we have calculators, so why we rationalize the denominator anymore is beyond me. We rationalize the numerator because it is a technique that we use to find the limit of a function. Let me show you. The limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. If I were to try to do direct substitution, I would have 0 in the denominator, which is a problem. Therefore, we're going to use this technique of rationalizing the numerator. So we're going to multiply both the numerator and the denominator by the conjugate of the numerator. So I've got the square root of x plus 1 that I'm multiplying the numerator by, and I want to just change the way this looks, not the actual value. So I'm going to make sure that I am multiplying by a factor of 1, and anything over itself is indeed 1. So this is going to give us the limit as x approaches 0 of the numerator, the square root of x plus 1 times the square root of x plus 1 is x plus 1. Negative 1 times positive 1 is negative 1. The outer and the inner are going to cancel out. And in the denominator, we have x times the quantity, the square root of x plus 1 plus 1. Let me give myself just a little bit more room here. And the limit as x approaches 0 of x in the numerator over x times the square root of x plus 1, there's some parentheses in there, plus 1. I'm going to do direct substitution, so I'm going to put a 0 in for x, a 0 in for x, and a 0 in for x. And that's going to give me the limit as x approaches 0. Actually, it's going to give me, I don't have to rewrite that because I'm actually going to compute the limit right now. So I've got 0 over 0 times the square root of 0 plus 1. No, 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 that's not what I have. These x's canceled out. So I don't have 0 in the denominator or the numerator, which is exactly what I wanted to avoid. I have a 1 in the numerator, a 1 in the denominator, and the square root of 1 plus 1. So that's 1 over 1 times 0 plus 1 is 1, and the square root of 1 is 1. 1 plus this 1 is 2. This is equal to 1/2. Now, if you find yourself with a 0 over 0, you forgot to cancel out your problem. Let's try another one. Let's do this one together. The limit as x approaches 0 of the square root of x plus 4 minus 2 all over x. You can see very clearly if I put a 0 in, I'm going to have a problem in that denominator. We can't divide by 0. Therefore, we're going to rationalize the numerator. So we've got the limit as x approaches 0 of the square root of x plus 4 minus 2 over x. And now we're going to multiply by the conjugate of the numerator. So I'm going to do that in the numerator and the denominator. And that's going to give me the limit as x approaches 0 of, in the numerator, we're going to have x plus 4 minus 4 all over x times the quantity, the square root of x plus 4 plus 2. Give ourselves just a little bit more room. The limit as x approaches 0 of x in the numerator over x in the denominator times the square root of x plus 4 plus 2 is equal to, the x's cancel out, leaving me with a 1 in the numerator. Now we can direct substitution in for x. We put that 0 in, and we get 1 over the square root of 4 plus 2. Now it's the square root of 4 because 0 plus 4 is 4. This is 2 plus 2, which is 4. 1 over 4 is our answer. Okay. Now, we've talked about one-sided limits. We've talked about one-sided limits. And in one-sided limits, we have from the left, and then we also have from the right. And we've talked about this when we were talking about this in particular. So if I were to say, what is the limit of this function as x approaches 1? What's the limit as x approaches 1 of f of x? Well, from the left side, our function value is approaching 2. From the right side, our function value is approaching 2. So from the left side, we would say the limit as x approaches 1 from the left, and if we were writing from the right, the limit as x approaches 1 from the right. And we put a little minus sign from the left, positive sign on the right. Now, the limit as x approaches 1 from the left is 2. The limit as x approaches 1 from the right is also 2. Therefore, the limit as x approaches 1 of f of x is equal to 2. If I say, let's erase this because it is beautiful, but I'm going to erase it. If we say, let's look at 0. From the left, the limit, I'm going to make this all green this way I don't have to keep changing. The limit as x approaches 0 from the left of f of x is equal to -2. So from the left, we're down here, down here, down here. It's -2. This is a -2 right there. From the right, it's +2. So the limit, let's give ourselves a little bit more room. The limit as x approaches 0 from the right of f of x is equal to +2. Therefore, because these are different, the limit from the left is not, I don't know what that x was, is not equal to the limit from the right. Therefore, let me extend the page. The limit as x approaches 0 of f of x does not exist. Does not exist. D-N-E. So let's take a look at these. I know it says a checkpoint, but we can do these together. The limit as of the function, right? The limit as x approaches 2 from the left. And we're talking about absolute value of x minus 2 over x minus 2. So we know that we come right to, right? And it's all about 2 right there. This can be written as x minus 2 over x minus 2 is the same thing as x minus 2 when x is greater than 2, and it's the opposite of x minus 2 when x is less than 2. So it's all about this 2 right here. So what's happening? Well, when x is greater than 2, I have x minus 2. Let me use some color here. I've got x minus 2 over x minus 2. This goes right in for that, right? So x minus 2 over x minus 2 is 1. So when I'm greater than 2, I'm just going to get a 1 out. However, when x is less than 2, so when my x values are less than 2, I'm going to have the opposite of x minus 2 over x minus 2, which is going to give me a -1. So as x approaches 2 from the left, I'm approaching -1. As x approaches 2 from the right, the limit as x approaches 2 from the right of this function gives us a +1. Now, the only way a limit exists is if the left limit equals the right limit. So if there is no left and right, then you have to test the limit coming from the left and the limit coming from the right and make sure that they are equal. So let's look at this graph. The limit from the left of 1 looks like it's headed towards 3. So the limit from the left, the limit as x approaches 1 from the left of f of x is equal to 3. The limit coming from the right of 1 looks like it is also approaching 3. I'm just going to save myself some room here. Since both of them equal 3, then I can say the limit as x approaches 1 without putting a left and right is equal to 3. It's pretty snazzy. Now this one you would have to draw. So let's draw this one. X squared plus 1, we know, is going to look something like this. Just sketch it. Beautiful sketch right there is fine. And then 2x plus 1, we know is up 2, right 1, something like that. We've got this going on. It's a piecewise function, right? So we've got a great big hole there. There we go. So there's our half, and then we've got, let's see, down 1, 2, and then left 1, and then we got something like that happening. And we want to know the limit as x approaches 0 of f of x. So in order to do this, we need to check the limit as x approaches 0 from the left. And that is equal to, let's see, from the left, looks like it's approaching this 1 right here. So from the left it's 1. And then from the right, it's also approaching that 1. So as x approaches 0 from the left of f of x equals 1, the limit as x approaches 0 from the right is also equal to 1. Therefore, the limit as x approaches 0 exists for f of x, and it is also equal to 1.